Hello everyone and welcome to another digital signal processing video. This video covers the inverse Z-transform via the partial fraction expansion method. Specifically, we'll look at how to take the inverse transform of a rational function of this form. If we have a strictly proper fraction, then we can say that x of z can be written as the sum of two components. One corresponding to the first pole and one corresponding to the second pole. And we have two coefficients, a and b, that we have to solve for using standard partial fraction expansion techniques. Now we note that these two components, the ROC for each of them is decided by the pole location. So the ROC for this one is z greater than a half, and the ROC for this one is z greater than a third. The overall ROC is the intersection of the two, because we're adding these together. So that's z greater than a half, and that's what we started off with. And then note that once we've split it up this way, we can easily take the inverse transform using the standard pairs from the table, and we'll just get that x of n is equal to a times a half to the n u of n plus b times a third to the n u of n. So the key now is solving for a and b. Let's go back here, though, and focus for just a second on what we mean by a strictly proper fraction. We mean that the numerator has a lower power in terms of z inverse than the denominator. So the power of z inverse in the numerator is 1, right? We have z inverse. If we multiplied through here, we would get a power of z to the minus 2 in the denominator, right? So this is a strictly proper fraction. And we're working in terms of powers of z inverse because that's how our standard table pairs are written. Now we need to solve for the partial fraction expansion coefficients a and b. If you've done partial fraction expansion before, say for the Laplace transform, this technique should be very familiar to you. The only real difference is now we're working in terms of polynomials written in terms of z inverse instead of s. So one way to think about how we solve for a and b is we multiply both sides of the equation by the denominator here. That leaves us with the numerator is equal to a times 1 minus a third z inverse plus b times 1 minus a half z inverse. Obviously, we've done some cancellation in that multiplication. Okay, so we can now say, well, what if we set z inverse? So if z inverse is equal to 2, then this term here will go to 0, and I'll just be left with minus 1 plus 2/3 z inverse is equal to a times 1 minus 1/3 z inverse, or a is equal to minus 1 plus 2/3 z inverse over 1 minus 1/3 z inverse. And remember, this is all valid when z inverse is equal to 2, okay, because that's what made this term go to 0. So if I just plug in here, I can solve for a. A will be equal to minus 1 plus 4/3 over 1 minus 2/3, and that ends up being a third over a third, which is 1. Okay, so we've just solved for the a coefficient. And then if we look at what we just did here, we can see a pattern, right? That basically the a coefficient was if we cover up this term that's associated with 1 minus a half z inverse, right? Cover up the pole associated with the coefficient we're looking for, then we're just going to be left with these two terms, which is what we were left with here, and we set z inverse equal to the value that of where the pole goes to 0, right, where that term goes to 0. So we can simplify what we're doing over here, and we can say b now. B is going to be the term associated with this pole. So I'm going to cover that one up, and I'm just going to rewrite minus 1 plus 2/3 z inverse over 1 minus 1/2. Write that a little more clearly. 1 minus 1/2 z inverse. And now z inverse is equal to the value that makes this go to 0, this pole term go to 0, which is 3. So z inverse is equal to 3, or z is equal to 1/3. That's the value of this pole here. And so I just substitute in, and I end up with b is equal to minus 1 plus 2 over 1 minus 3/2. So that'll be a 1 in the numerator and a minus 1/2 in the denominator, so this will be minus 2. Okay, so now I have my two a and b coefficients. Once I have the a and b coefficients, I can simply substitute them into this equation over here, and I end up with the expression I need for x of n. I just put in, for a, I put in 1, and for b, I put in minus 2. So it's minus 2 1/3 to the n u of n for this term, and 1 times 1/2 to the n u of n for that term. So that's my final expression for x of n for this problem. So now one other thing we have to cover is what we do when x of z is not strictly proper. So here's an example of a rational function that's not strictly proper. The maximum order of z inverse in the numerator is 3, right? I have z inverse to the 3 right here, and the maximum order in the denominator is 2. So this is not strictly proper. So we have to use long division then to make this fraction strictly proper. So to make this fraction not strictly proper, we're going to use long division, and I'm going to write the long division like this. So I'm going to write 1/6 z to the minus 2 plus 5/6 z to the minus 1 plus 1, and that's going into this fraction here. And so I'm going to write that as 1/3 z to the minus 3 plus 11/6 z to the minus 2 plus 3 z inverse plus 1. Okay, and this is how I'm going to do the long division. And the order that I've put these things in is important, because I need to set up this order correctly so that I'm getting, I'm going to end up with a fraction that is strictly proper. Okay, so if I do this long division, right, I put in here, well, to get this value here, I will have to get 1/3 z to the minus 3 out of this, I have to multiply by 2z inverse. So that's my first entry there. So if I multiply out and I put in what I'm going to subtract off here, 2z inverse times 1/6 to the z minus 2 gets me 1/3 z to the minus 3. And then 2z inverse times 5/6 z inverse will get me 10/6 z to the minus 2 plus 2z inverse. Okay, and then I'm going to subtract that off. I subtract it off. This term goes to 0. 11/6 z to the minus 2 minus 10/6 z to the minus 2 gets me 1/6 z to the minus 2. 3z inverse minus 2z inverse is z inverse. And then 1 minus 0 is just 1. Okay, so then I have to go the next point, right? I'm going to have to do this 2 times because this factor is 2 times has an order that's 1 greater than the denominator, right? And for it to be strictly proper, this has to be an order 1 less than the denominator. Okay, so I go through this process again. Now I need to get a 1/6 z to the minus 2. Well, that's what I have over here, so I could just add 1. So 1 times 1/6 z to the minus 2 will be 1/6 z to the minus 2. And then 1 time, that'll be plus 5/6 z inverse plus 1. Okay, so again, I subtract off here. And what I'm left with, 1/6 z inverse z to the minus 2 minus 1/6 z to the minus 2 is 0. Z inverse minus 5/6 z inverse is 1/6 z inverse. And 1 minus 1 is 0. Okay, so I have now subtracted this off, and I can see, hopefully, that I'm going to end up with something that will be strictly proper. So I'm going to end up with x of z is equal to 2z inverse plus 1 plus 1/6 z inverse over 1 plus 5/6 z inverse plus 1/6 z to the minus 2. Okay, so I end up with this expression here. Now I've got these two leading terms out front, which are pretty easy to take the inverse transform of, and I've got this expression here, which is now a strictly proper fraction. Okay, so now this is the problem I have to solve. I've done the long division so that I now end up with two leading terms plus a strictly proper fraction, and I started off knowing what the ROC was. So now I need to do partial fraction expansion on this and then take the inverse transform of the whole expression. So I encourage you to pause the video here and solve this problem for yourself, and then rejoin and see how I solve the problem. Okay, hopefully you've solved the problem for yourself, and now we can compare to my solution. So I have, remember, we started with this expression here. I need to factor the denominator here. So we can factor the denominator, and that splits into two terms, 1 plus 1/2 z inverse and 1 plus 1/3 z inverse. If you multiply that back through, you get this, right? So we factored it, and now it's in a good form to do partial fraction expansion, because again, the power of z inverse here is z inverse to the 1. The power of z inverse here is z inverse to the 2 in this denominator. So this is strictly proper. All right, so now I know I can use my standard partial fraction expansion techniques to split this up, and I've just gone ahead and solved for the a and the b coefficients here that I get for this partial fraction expansion. Okay, now I know that I already know what the ROC is associated with each of these terms, right? My overall ROC is z greater than 1/2, so this term is associated with z greater than 1/2, and this term is associated with z greater than 1/3. And let me write that more clearly. So this is z greater than 1/3. The intersection of these two gets us that ROC. But then when we take the inverse transform of these terms, we get our standard pairs here. So we just get minus 1/2 to the n u of n and minus 1/3 to the n u of n here, right? With the leading coefficients being minus 1 and 1. It's minus 1/2, right? Because remember, the standard pair that we're relying on here is a to the n u of n has a transform pair 1 over 1 minus a z inverse. And that's z greater than absolute value of a. A here for this term is minus 1/2. A for this term is minus 1/3, little a. So we get these two terms automatically from our table, and these easily proceed from the table. They're just two individual points in the sequence. So we've now solved for the inverse transform of a signal that had a non-proper fraction to start with.